Oh, no, here it is. Here it is. Yeah, it is. I think it's.
This one's nice because you can see the WebEx is a laser. Change the pointer like a red dot to make it look like a light thing. Go to a point. Right. If you want to.
Yeah, yeah, yeah. Oh, yeah. I think I've seen that one and used it. Are we on WebEx? Let's get that.
We're on WebEx, but the audio is not yet like. The audio on? It is now.
Yeah. Okay.
So we mute WebEx up there, which blocks all the audio going down. So it's on right now.
So Kevin, can you hear us? And we can see you well.
Okay, yes, I can hear you just fine. Can you hear me?
Yep, hear you fine as well. And
Great.
so you can start sharing whenever, and we'll get started at little past 9. Maybe give a couple of minutes for people to come in.
They're still having breakfast.
Yeah, yeah.
Okay, sounds great.
So once we so. This one? On the WebEx, here we are. This one. Yeah. Okay. Okay. We'll get started in a couple of minutes. People wandering in. Okay, good morning. So let's get started. Last day of this workshop. So today we're going to start off with 3 talks and then transition into a Hab Worlds hack session and other parallel sessions, and the coffee break will be at 11 o'clock. And the first 3 talks are like 20 minutes each. So we start with a remote talk from Kevin France. Young stars and their circumstellar environments with future ground and space-based observatories. So go ahead, Kevin, take it away from there.
Okay, thanks very much, Robbie. Good morning, everyone. Apologies I couldn't be there in person today. I've been following some of the talks and on the Slack. It sounds like it's been a really great workshop so far. So what I want to tell you about today is looking beyond Ulysses, and this sort of long title here about the observational landscape of young stars and their circumstellar environments with future observatories. So I was asked to talk about future ground and space-based observatories, and I'm going to do that, but you're going to get a little bit more on the space-based side just because of my bias here. So what I ultimately want to talk about today is how we get from this picture, where we have the Hubble Space Telescope observing a young star with a disk, to the future, where we have something like the Habitable Worlds Observatory, or something like this rendition of the Habitable Worlds Observatory that's observing a much larger number of these sources and giving us new insights on mass accretion, the outflows, and molecular material in protoplanetary disks. So here's what I'm going to talk about today. I'll do a little bit of background on the rich UV spectra of classical T-Tauri stars. You've seen a lot of this week, so I'm just going to touch on some of the highlights. Then I'm going to look ahead to what we can do with future missions and ground-based observatories at kind of the medium to large scale. So I'll look at future directions for mass accretion studies in both the UV and the X-rays, talk about chemical abundances, both in the UV and the infrared, and then optical near-infrared prospects for detecting and characterizing protoplanets. Then I'll focus the last couple minutes of my talk on the Hab Worlds Observatory. I know you have a session on that later this morning, and I think you've heard a couple of talks about this where we see this as the future for both massive and low mass stars. So I'll talk about the UV capabilities specifically, and then I'll end with some QR codes that actually will give you the ability to jump into some of the work groups that are ongoing for Hab Worlds today. Okay, so maybe you've seen this one before. Okay, I can't hear you, but I'm assuming that you're laughing at that. So I wanted to take the first couple of slides to sort of lay out the framework again. I know you've seen this fantastic figure many times. So what I'm going to talk about in these intro and then sort of lead into the open areas where we can address with future missions is the UV and X-ray emission from the accretion regions. Staying, that's sort of in the inner few tenths of an AU, then moving out into the disk, out to a couple of AU, the UV molecular spectra, probes of abundances and outflows. And then as we move out beyond the UV into optical and IR wavelengths, they're the tracers out here for photochemistry, gas masses, and the detection of young planets in these disks. So I won't show this anymore. We'll get away from here. So again, this is, my bias is space-based in UV, so I'm going to focus mainly on what we're seeing in our UV spectra. So I wanted to take just a moment, and maybe you've seen an example of this already. I didn't see it in the other talks, but just to remind all of us how incredibly rich the far ultraviolet spectra of a protoplanetary disk is. So this is, I'm gonna scroll this by you. This is one of our best spectra from HST COS of a young star disk system. And here, as you'll see as we go through, I've highlighted a couple of different H2 transitions CO emission, strong atomic lines tracing accretion in the underlying stellar chromosphere, and then also some outflow lines from similar forbidden species. So I'm going to let this roll. And you'll see that as we go across, there are just hundreds and hundreds of emission lines, also lots of absorption lines, but you don't see in this particular spectrum, in every one of these disks. So the combination of the strong mass accretion, the molecules in the disk, and how those two interact with each other leaves this incredibly rich disk spectrum that we see in almost every gas-rich disk. So in one of these UV optical spectra, we have tracers from these different environments. We can see the underlying very young pre-main sequence star itself. So we get tracers from that, shown a couple here. We get, this is probably the best place to understand and quantify mass accretion rates, as you saw in a number of the talks earlier this week. And then the rich molecular spectra, which is sort of essentially the far UV range, that includes both bound and outflowing molecular material. So this is an older figure from Laura Ingleby's paper from about a decade ago, but Kaylee Pittman has shown a couple of these plots. I think you saw this in Catherine's talk as well. So this is the idea where we use the excess near UV, in particular emission, to quantify the mass accretion rate. I think there's directions to go in the future, and I'm going to sort of touch on this in the next few slides. One of the things that's still a work in progress, I think, is really to understand how this connects to the far UV continuum that we observe in most of these disks. And then a big open question is, what are the impacts of the dust attenuation? So that's both circumstellar and interstellar dust. It's a very hard thing to quantify, and quantify in both the actual shape of the dust attenuation curve and its amplitude. So I'll talk a little bit about that in future missions. Of course, this is really important because this is the emission, as I think you heard in some of the talks yesterday morning. This is the emission that drives the dispersal of protoplanetary disk and is also driving the evaporation of the outer atmospheres of the youngest planets. We're starting to see some hints of this in transit observations of very young planets now. And of course, ultimately, once the disk is dissipated, this high energy radiation from the young star is what drives atmospheric loss from these young planets, which drives the distribution of the extrasolar planet demographics that we observe today. So to come back to this really rich spectrum, let's look at the UV molecules. So there are, depending on the richness of the disk, tens to hundreds of photoexcited H2 lines. These are pumped by Lyman alpha photons in every gas-rich disk spectrum. So this is one of the signposts for active accretion, is this, the presence of these molecular hydrogen fluorescence lines. One of the surprises that we got in the early days of HST COS was that there are also CO fluorescence lines that show up in about half the disks. And also this 1600 angstrom bump, which is the kind of informal name that some of us use to refer to this water dissociation feature that's seen in the molecular spectra here. So where are we going to go with this in the future? So we're still limited to tens of disks, even with Ulysses, where we now have maybe 100 that show the H2 lines. Most of those disks are not, or most of those observations are not sensitive enough to give us high fidelity CO and water spectra. So we really want to get statistical samples of these disks to understand how these molecular tracers in the UV connect to the dust properties and how those things evolve with the dust disk. And then, of course, the connection to the photochemistry we're seeing in the MIRI spectra now. This is also important because we use these lines to infer the radial properties of the radial distribution of this gas. So this is some one-dimensional code that Carrie Hoadley developed, and I think you saw us a little bit about this in Nicole's talk afterwards, about how we use these lines to infer the radial distribution of molecular hydrogen, and at least the hot molecular hydrogen in the disk surface. More recently, we've been using these same lines and taking advantage of advances in the HST COS wavelength stability, wavelength solution stability, to start to probe molecular outflows in these lines. Some of this work has been done by our group. This is something from Matt Kalsher, who's a grad student at Colorado, as well as the group in Rome that's made some nice comparisons between these lines and the infrared lines of H2. So we can compare these outflows in the UV H2 diagnostics to sort of the more traditional disk wind emission diagnostics from forbidden oxygen. And we've shown that here, where the blue points are the H2 and this single and broad or narrow and broad components versus the O1. And what you're seeing is we're really seeing that most of these disks are, depending on the H2 transition, most of these disks are actually showing molecular emission in their winds now. Again, this is really thanks to the improved wavelength calibration of COS. This is something we talked about doing in the early days of COS, but weren't really able to. So where we'd like to go in the future, we'd really like higher both spectral and spatial resolution, as well as this strong wavelength stability to be able to measure the 3D distribution of this material. Okay, and then last thing I'm going to say is about using line of sight absorption studies through these disks to study molecular abundances. So we've also things that we were unable to do previous to COS was probe the material and absorption through these disks. So here are just two examples of molecular hydrogen absorption down at the shortest wavelengths that were enabled by some of the blue modes that were developed for COS, as well as CO A to X absorption in the disks. And so for a very small number of these disks, we've been able to use the kinematic and temperature information to directly measure the CO to H2 ratios in a handful of these disks. What we've really been limited by is the sensitivity to be able to see these profiles, these line profiles at high spectral resolution and signal to noise. So we'd like to be able to go to deeper observations of these. Okay, so where do we go from here? So I'm going to talk in just a few minutes about the new medium and large scale missions that are either in development now or will be selected sometime in the next year. We'll talk a little bit about ELTs and how we are going to use those particularly to find protoplanets. And then we'll talk about really the super Hubble Space Telescope future, which is the Habitable Worlds Observatory. So let me mention a few things that are coming down the pipeline. So the UVEX mission was just selected by NASA. This is the next MidX mission, just selected by NASA a few weeks ago. So UVEX has low resolution spectroscopy in this 115 to 260 nanometer wavelength range. Also has all-sky FUV and NUV imaging capabilities that would be an enhancement on what we had from GALEX. So this will be great for finding new accreting sources. But really, I think what's interesting here is the ability to survey lots of sources at low resolution that will allow us to do extinction studies towards these stars, where in the past we've really even struggled to find the right targets to do this. When we start talking about all-sky capability, we'd really like to be able to get down and look for instance, the 2175 angstrom bump and the extinction curves through star-forming regions. So I think this is, UVEX is scheduled to launch later in this decade, and this is going to be an exciting way that's going to help us quantify the output that we're seeing from these young stars. Thinking a little bit about accretion, this is a simulation from the ARCIS probe mission that is one of the probe concepts that's being reviewed by NASA now. So ARCIS is a joint UV and X-ray spectroscopy mission. And so with ARCIS, you should be able to measure the differences in line profiles that allow you to infer different paradigms for the mass accretion, the actual physical transfer of material onto the disk. This is something that we could basically can't do in the X-rays. Here is an example of 500 seconds of Chandra time trying to look at the 07 transition, whereas in 5 kiloseconds of ARCIS X-ray spectroscopy, we should be able to separate these two different accretion scenarios. Similarly, in the UV, this is an 06 line. This is something that we could do with FUSE in 15 kiloseconds, but in a simultaneous 2 kilosecond observation from ARCIS, we should be able to strongly differentiate and make a high profile, high fidelity line profiles simultaneous with the X-ray and the UV. I said that already. So similarly, for another probe mission that's under study, this is the first mission. So this is a far infrared spectroscopy mission that has access to the rotational ladder of water. So this should be really great for studying the disk chemistry of young stars and their disks, as well as, so I show water here, but also first is designed to be sensitive to HD, which should allow us to get molecular disk masses without the same degree of uncertainties that we have when converting from CO or its isotopes. Looking towards the ground, this is the ELTs are coming. There's a lot that's to be excited about with ground-based telescopes as we begin to push towards high contrast, strong AO systems that operate in the near infrared. So one of the things I think is most exciting here is beginning to probe down into the structure near infrared wavelengths of the inner disk and being able to make statistical studies of protoplanets around these pre-main sequence stars. These same instruments will also be fantastic for doing spectrostrometry of CO and water in the environments of these young stars, as well as molecular wind disk surveys. So, we have large samples of these in the forbidden oxygen lines now. As we start to push towards CO and water, we expect to see some of these also in there. And then as we go to shorter wavelengths, we really need to go to space to start looking for circumplanetary accretion. So here's a simulation that we put together for the LUVOIR study a few years ago. So this is a narrowband H-alpha image showing scattered light from the disk and circumplanetary accretion from a protoplanet at 30 AU from a young star. So I won't talk about really about the details here. But as we push to shorter wavelengths, we should begin to really study the circumplanetary accretion environment around a statistical number of young stars. So that's going to take me to the last thing that I want to talk about today, which is pushing to shorter and shorter wavelengths with future observatories. And that takes us to the Habitable Worlds Observatory. So as you know, HabWorlds is the NASA's response to the number one recommendation of the 2020 Decadal Survey. So it is a large UV optical infrared mission that both does what we call transformative astrophysics, as well as searching for the signs of life on rocky planets around other stars. So really searching Earth-Sun analogs in a way we can't do with other facilities. So notionally, again, all of this work is being developed by the NASA's START and TAG teams with a huge amount of community involvement that I'm going to tell you about in just a second. But we notionally have 3 instruments that we imagine for HabWorlds fed by a roughly 6-meter telescope. So there'll be a coronagraph to find Earth-like planets, wide field imaging. I was actually at the START and TAG meeting earlier this week where we sort of mocked the idea of 3 arc minutes being wide field, and a high resolution multi-object UV spectrograph. So let me tell you a little bit about the capabilities of the UV spectrograph since we're talking about where to go from Ulysses. So the current working design for the HabWorlds spectrograph is built off what we call the LUMOS instrument that was part of the LUVOIR study. So this instrument has multi-object spectroscopy, which I'll tell you a little bit more in a second. Roughly 2x2 arc-minute field of view with resolving powers as great as 60,000 in the multi-object modes, as well as FUV imaging over a similar field of view with a suite of broad and narrow filters. And what's not shown in this particular schematic is high-resolution point source spectroscopy, not multi-object mode, but resolving powers somewhere between 100 and 120,000, between 100 and about 170 nanometers. Okay, so talking about the increase in sensitivity, here's a plot that Eric Lopez made for the LUVOIR study. So what we're talking about now is the effective area, which is this middle curve here. But these are the effective area increases compared to their comparable modes on HST today. So we're really talking about a transformative shift in just our light collecting power alone. And on top of that, these are going to be multiplexing. This is going to be a multiplexing instrument. So don't read all the stuff in the table here. This is just to give you an idea using the same nomenclature as we're used to from Hubble, what the types of resolving powers over a couple of arc-minute field of view, and simultaneously what their angular resolution is in milliarc seconds. So we'll do this probably with a microshutter device, which is going to be an improvement on what we have on JWST NearSpec now, where we're able to get hundreds of individual objects in every observation. So let me show you a quick schematic of how this would work, and then I'll wrap up in a moment. So if we look into a field, say a star-forming region like Orion, we can go in and get spectra of anything of interest in that particular field. So we can go in a disk or in a star-forming region like Orion and identify, say, 50 or 100 interesting young stars that are in there, and get high-resolution spectroscopy of all of those stars simultaneously. So this is actually showing the simulation showing two different grading modes, the final co-added data from two different grading modes. It's allowing us to measure, in this example, water and molecular hydrogen through the disk surface at the same time. Okay, so let's see, showed that already. But you can imagine that as we have higher and higher sensitivity, we can probe ever deeper in the disk surface. So we won't just be limited to things like H2 and CO. We should be able to get down to water, methane absorption, CO2 as we probe deeper and deeper into the disk. So the last thing that I'll sort of leave you with is what I imagine as we go with high sensitivity is going to allow us to do this for many, many thousands of disks, where we're kind of stuck at around 100 today with HST. So this is going to give us a wide distribution of viewing angles and sight lines through the disk. So we're going to be probing photoevaporative and MHD winds. As we look through at different inclinations through the disk, we're going to be sampling the warm disk atmosphere. Some of our disks are going to probe down into the molecular surface layers that we're seeing with JWST. And then for probably a handful of deep dive disks, we're going to be able to look, starting to look deeper now. Now, of course, not down into the midplane, but AVs of several, where we're beginning to get more complex chemistry and possibly in the region where grain growth is taking place. So this is really going to allow us to build up what I call a four-dimensional picture of the disk surface, both in radius, height, wavelength, but also these things all change in time. So we're also going to see how these the molecular content evolves with, say, Dipper phenomena and things like that. Okay, if you want to get involved with Habitable Worlds, stick around later for the hack session. You can sign up with this QR code here. There are a ton of science and technology and joint science and technology working groups that are going on right now. We really encourage, I think we have over 1,000 people signed up now for these different working groups. So there's a lot of excitement and a lot of work to do to make this possible. Of course, if you're going to get engaged, I want you to sign on to our code of conduct. All right. And in summary, I'm out of time, so I'll just wrap up by saying that Ulysses has provided this amazing new framework to understand young stars and their environments. You've seen fantastic talks this week about that. There's going to be a lot of exciting stuff to do with future missions that are either coming online later this decade or early in the 2030s that are going to touch on all of these aspects. And then the thing that we should be really, really excited about on the longer term horizon is taking all of these things to kind of the order of magnitude or 2 order of magnitude next levels with the Habitable World Observatory. So thanks for your attention. I'm glad to take questions.
Thanks, Kevin. We have time for maybe a question or two.
Thanks a lot, Kevin. I have like a programmatic question. So we're about to have this hack session to maybe draft some precursor science cases for hub worlds in response to, I guess, the proposal call from NASA, for which the NOI is due in a couple weeks. You presented some possible, hub world science cases there. I find that there's like overlap between what the working groups, the science working groups are doing, drafting science cases, and then what the call to the community about drafting precursor science cases are. So is it still worth submitting cases to maybe investigate, you know, like the science requirements that would be needed to achieve these things that you just presented with Hub Worlds, or should we just let the working groups do it? Yeah.
I think that was Julia. Yeah, that's a great question. So I'd say yes, absolutely. Please put in for the precursor science. So the difference that I see is what the working groups are doing right now, the existing and that I hope everybody's signed up for, Hab Worlds working groups, are looking at the science that Hab Worlds can do, or the science that we want to make sure that the mission can do. The precursor science has a pretty specific focus of work that we can do now that might influence how we design that mission. If we need to know, for instance, lab-based astro to have better cross sections or something that's going to tell us if we need a certain wavelength range in an instrument. So these really looking for things that influence the architecture of the instrument or the telescope. So I think those, at least from my understanding from headquarters, that's really what they want to focus on for the precursor science cases. I think you can look up the ones that were selected last time. Some of them were for Hab Worlds, but also some of them were about the X-ray or far infrared future grade observatories, but that things we need to do today to understand what the requirements are going to be for that mission.
Okay, great, thanks. So let's thank Kevin again and move on and continue the discussion on Slack and later on at the Hab World session. So we're going to start sharing here, and let's thank Kevin again. Yes. No, don't end the meeting. No, let me try this. So let's first get to.
So do I need to share or how?
Yeah, we'll share. So first, if we put up.
So this is my presentation.
That's it. Yeah, if you just set that up, and we go to WebEx and try not to get out of the meeting.
And share screen.
Just share. There it is. And then we can do the slideshow.
Can you hear me? Yes. Yeah, I clicked here, but it's not working. Okay, now it is.
Okay, excellent. So our next talk is the future, next generation observatories and prospect for massive stars. Miriam Garcia, take it away, Miriam.
Hi.
And 20 minutes. Yeah, 15 for the talk and 5.
Yeah, well, thanks for the survivors of the dinner and the karaoke for being here. I would try to get you excited with this topic, which is very exciting to myself. First, a big thanks to everybody who have helped me with this talk at some point. And this is going to be the outline. I'm going to speak a little bit of some next generation observatory. You will realize this is a very biased view for 2 reasons. One, I'm European. Second, I work on massive stars that are far away, and I need a big collecting power. So that's going to introduce a couple of biases in the talk. And then I will do the other way around, as Kevin did, and I will talk about the big open questions that hopefully we will be able to answer with this. So, sorry, this is still an old picture of Le Voir, but yeah, we were all very excited when the decadal survey results came up, recommending this large facility with capabilities in the ultraviolet, the optical, and the infrared, which, at least to me, constituted the really, truly successor to Hubble Space Telescope. I was not so happy to read about the aperture diameter, which in principle it was 6 meters, but as Kevin said, this is circumscribed. So actually, Hub Worlds is going to be similar to Le Voir B. And we just heard Kevin's talk, and it's going to have a chronographer, the imager. Sorry about this. Spoiler. Yeah, let me try to find the mouse. Okay, but you can see this one, right? Yeah, and so we were going over the instruments of Hub Worlds, and since I'm European, I'm going to talk about a little bit more on Pollux. So Pollux was supposed to be the European contribution to Hub Worlds, and it was going to be a very high resolution spectropolarimeter that could do polarimetry in the eye, Stokes eye and intensity and circular polarimetry with very high precision. So the stage at the moment is that the Pollux team has reassembled in Europe. We will be submitting a project to NASA to try to stay linked to Hub Worlds, but we don't know what's going to happen because we don't know if there's going to be room for this in the final observatory. And also, LUVOIR B is off axis, so this increases the number of reflections, and this, of course, in the ultraviolet is a problem, although if we have awesome coatings, we could circumvent this. There's also another possibility. This is the World Space Observatory. This has been delayed ever since I came into the game, so we really don't know what's going to happen with this one. This is a Russian space observatory with a strong participation from Spain, and it would have high resolution spectroscopy, medium and low resolution spectroscopy. Of course, it will have an imager, and there is this latest contribution by JAXA, the Japanese agency, with a spectrograph to look for hydrogen and oxygen in exoplanets. But we don't know the situation. We don't know what's going to happen with this. And again, since I'm European, I need to talk about our 39-meter extremely large telescope, which is going to have 3 first light instruments. I highlight here 2, the ones that may be more relevant for massive stars. One of them is the first one is the infrared imager that is aided by adaptive optics, obviously. And the second one is Harmony, which is a very high spatial resolution integral field spectrograph that could reach the 4 milliarc seconds per pixel. But because I work on faint stars, my main interest is in MOSAIC, which is a generation 1.5 instrument for the ELT, and basically it's a very wide field multi-object spectrograph that will work in the optical range all the way to the H-band. Some people, we are working very hard to push this limit down to 4,000 angstroms, since for massive stars, they contain most of our diagnostic lines, and the resolution will be 4,000. And the nice thing is that it will be able to observe up to 200 objects simultaneously, and it will also have 8 IFUs. But since this is not enough, there's been recently this initiative. This is a telescope in really its beginning stage. It's called the Wide Field Spectroscopic Telescope. It's a devoted telescope only for spectroscopy. So it has a very wide field IFU of 3 arc minute times 3 arc minutes. Muse is 1 arc minute times 1 arc minute, so this is really big. And then it will have this humongous multi-object around. I think it's driven by fibers. So we really can do dwarf irregular galaxies in very quick time. Okay, so that was for instrumentation, and now for the questions. So if you've seen the talks of mine, you may have seen already this slide. So here is to highlight that massive stars play an important role at many stages of the history of the universe, beginning maybe with the first stars. Some people think that the first stars were thousands of solar masses. I'm a bit skeptical. But anyway, massive stars began reionization. Some of them might have died by very instability supernova, causing very early chemical enrichment. And if you don't want to go to the extremes, if we want to study star-forming galaxies, the ultraviolet set is going to be dominated by massive stars. And of course, massive stars are also linked to gravitational wave and some other things we are currently working to explain. So we need massive stars. We need to understand their evolution. We understand their properties, effective temperatures, and luminosities in order to be able to consider that feedback. And we thought we had more or less figured this out. So this is an HR diagram with tracks. And here I marked the different phases of massive star evolution. In the main sequence, we have orbit dwarfs. And then post-main sequence stages include blue supergiants, red supergiants, luminous blue variables, and dwarf rayets. And at some point, our models also predict that they are going to explode a supernova. But the mounting evidence is that this is not so clear anymore. And if we don't know this, we will not be able to calculate feedback for massive stars for all these fields. So we really need to work this out and to understand why we don't know everything yet. And I've highlighted here 4 main reasons for that. There are more. First one is that we need to understand radiation-driven winds. The second one is that most of massive stars are born in binary systems that interact and make evolution very messy. Then magnetic fields. And finally, that we do not, we cannot characterize yet what's the role of metallicity in the evolution of massive stars in the very low metallicity end. So what's the deal with the radiation-driven winds? We've heard this many times during the workshop, but basically we have a wind driven by radiation. So the most luminous is the star, the stronger the wind is going to get. So this is basically what's shown here. And also the absorbers for the radiation energy and momentum are metallic ions. So if you decrease the metallicity, you're going to have a weaker wind. But in the end, what you are doing is removing mass from the star. And that has a strong impact on the evolution. And that's what I show in the central picture. So these are evolutionary tracks for solar mass, 60 solar mass star born with the composition of the Milky Way, the LMC, and the SMC. And you see the temperatures and the luminosities are very different. And this is going to translate into feedback. And now if you go, it's not shown here, but if we go to even lower metallicity regions, we can have this chemically homogeneous evolution. Find Dory, she can tell you all about it. She's an expert. And this is very interesting because it's one of the proposed channels to form 30 solar mass double black holes. But okay, so it's not only about feedback, but if you have a different wind, you will end up with different masses at the end of evolution, and that's what I show in the final picture. And this determines the type of supernova explosion you are going to have and whether you will have a neutron star or a black hole. Okay, so winds are important. You may have seen, we have seen this picture many times along the workshop. Oops, not this one. But ultraviolet has many, many diagnostics for the wind. So to me, I've been fighting for this. We need the ultraviolet to characterize the winds of massive stars. To me, Ulysses, if I had a word on it, Ulysses would have also reached the Milky Way. We know many more stars in the Milky Way for which we don't have the ultraviolet, and until we have the ultraviolet, we will not have complete winds. So we really need ultraviolet. And we have all these open questions that we've been hearing through the workshop. We don't know if there's a stability jump or not. The relationship between the wind momentum and the luminosity is we still don't get it. We don't know what happens in the high luminosity end. Yorick is another expert. We don't know what happens in the lower metallicity end. We don't know how to treat inhomogeneities. We don't know if it's smooth clumps over the wind, or they are big chunks, or if it's porous in velocity or not. Or, as Jun Sungqvist said, maybe we should forget about all that and just migrate to a 3D treatment of the winds. We don't know. We need observational constraints more than ever. And for that, Space Telescope, Hubble Space Telescope is going to be critical. But of course, at some point, we will need faster integration times, or fainter targets. And for that, hub worlds is going to be great. And another point is the structure and variability. There exist these narrow absorption components, like I show here. These are very narrow absorption lines. So if you do time series, they migrate toward the blue edge of the p-SIGNI profile. And again, we don't know what's causing this. We don't know if it's clamping, inhomogeneities, the magnetic fields, or what. And I'm European. So for this, Pollux-B on hub worlds would be great because we would be able to get very high signal-to-noise ratio observations in very short timescales, and we could trace the evolution of these kind of structures with time, and we could do polarimetry. We could see magnetic fields are involved. Okay, binaries. So some 10 years ago, the massive star community finally accepted that most of massive stars are born in binary systems and that they will interact. And the results from the gravitational wave experiments made it harder for us to turn our backs on this fact. So now we are having a new view of the HR diagram. This is a similar one to the one that I showed before, but now we are seeing binaries everywhere. So the upper main sequence and the blue stragglers could be binaries, or sorry, products of binary mergers. Same thing happens with the red stragglers. The LBBs could also be the product of a binary interaction. The low mass warp riots are actually not warp riots, but stripped stars. We need to reinterpret this diagram. And of course, it's very interesting to find a companion, but sometimes they are elusive. And I don't know if you remember the case of LB1. Some team reported that it was a 70 solar mass black hole, which was tremendous. And it turned out that they hadn't found the companion. And ultraviolet can help a lot with that. So this is a spectral energy distribution of a composite system, and what it shows is that maybe in the optical range you will not be able to see the companion, but if it's hot and it's stripped, I should have said that what's happening here is that the mass donor, the most massive component, is stripped of its envelope and it donates it to the secondary star. So we are left with a very compact and hot mass donor, and that's the one we could see in the ultraviolet. And there are some already successful experiments about this. Lee Patrick is looking for the hot companions to red supergiants. Maria Draut and Ylva Gottberg are identifying these stripped stars from the UVXs. And of course, we heard from Varsha's talk that we could characterize this, the stripped companion, if we have sensitive enough and ultraviolet spectra. So again, hub worlds can help a lot with this by identifying the hot companions with the wide field imager, and of course by doing the characterization with the spectroscopy. I'm a bit behind, sorry. So magnetic fields. The situation with magnetic fields is similar to what happened with binary stars a long time ago. They complicate our life by a lot, so we decided they do not exist, but maybe we cannot ignore them anymore. There have been some important surveys on this. We know that they affect more or less like 10% of massive stars. Few of them are of the order of kilogauss. Most of them are weaker, which makes them harder to identify. And they do not correlate with the stellar properties, and that's why we think they are mostly fossil, meaning the magnetic field is inherited from the gas cloud. Or in some exotic cases, maybe it could be formed from the interaction of two stars. But the fact that we are not detecting magnetic fields in 90% of stars doesn't mean they don't exist. We don't know. And also, they are very important in the post-main sequence stages. And I will say why in a minute. So what magnetic fields do is that in the stellar interior, they mess up with the angular momentum transport. That's rotational mixing and so on. And in the outside, magnetic fields interact with the wind. So that means, this results in a breaking of the star. They break the rotational velocity, and also they can confine the wind. So forget about all this, but the last line is important. We could form 25 solar mass black holes at solar metallicities, and thanks to magnetic fields. Otherwise, the wind is too strong, and the star is not going to end its life so massive. And of course, we need to know what happens after the main sequence, because maybe this could be related to the magnetic fields that neutron stars shows, and also to the formation of magnetars. Again, forget about this. These are detection methods. But basically, what we need to detect magnetic field is very high resolution spectropolarimetry to study the polarized components of the Zeeman lines. And finally, the field that's more dear to my heart, very metal poor massive stars. And I'm going to quickly go back to this scheme, where I hope I convince you how important massive stars are along the history of the universe. And I would like to draw your attention to the line of time, which roughly corresponds to the line of metallicity, from zero metallicity after the Big Bang to an approximate solar composition today. And if we draw a line where the SMC metallicity lies, is here. And we have here galaxies, transients, open questions. We don't have observables to work with at the moment. We need very metal-poor massive stars to inform this kind of studies. And to interpret the data we are collecting with James Webb, the data that will come with Rubin, and the results from gravitational wave observatories. And that's why, for many years now, I've been working on this, what I call the roadmap to the early universe, which basically consists on studying massive stars in dwarf irregular galaxies with poorer and poorer metal content, until hopefully one day we will be able to extrapolate the properties of massive stars to zero metallicity. What's the problem? That they are all very far away. This was just a summary of the situation, saying that at the moment we know 200 very metal-poor massive stars at most, maybe 230. We are doing big efforts with the biggest telescopes on Earth. This is not enough. What do we need? We need this nested strategy. First, we need to make the census. It's not enough with photometry. Photometry can guide us, but we need a spectroscopy to confirm that a massive star is a massive star. Okay, we don't need very high spectral resolution for this or signals to noise ratio, but we need to make the survey. And then we want to determine the stellar properties, we either need to increase the resolution or the signal to noise ratio. But if we want to do abundance stellar evolution, then we need to do abundances, because abundances are the telltale of the mixing that happens in the stellar interior and many processes. And for that, we need high spectral resolution and high signal to noise ratio. And of course, to get the wind, we need the ultraviolet, which is hard to get. Sorry. This one is hard to get because of extinction and because of the oversubscription factor of a space telescope, which we know is high. So what are the future prospects for this? I think for the first step, we can still do with 10-meter telescopes on the ground. But to really understand the evolution of very metal-poor massive stars, we are going to need the large collecting power of hub worlds and the ELT. So these are just some numbers. Of course, Mosaic at the ELT will be able to reach the local group, which let's say it ends at 1.5 megaparsecs. But I wanted to draw your attention to this. So this is a portion of sextans A. And what I'm showing here is that for each one of these circles, you will only be able to allocate one of the fibers of Mosaic. So it's not a huge gain in multiplexing. And also, the observations in the optical range are going to be scene limited. So I know it's not in the plan, but for my wish list, I wish there were multi-object optical capabilities for hub worlds, because adaptive optics are not going to work well in the ground in the optical range. So this is a niche that will not be covered. And yeah, so I don't know if we still have time to do this, but really I wish to push Lumos capabilities to the optical range. And of course, hub worlds will be fundamental to study the winds of very metal poor massive stars. Here I have done some estimates based on my own observations on IC 1613. So I put these stars farther and farther away. So if reddening doesn't kill us, we will be able to use hub worlds to study the winds of very metal poor massive stars out to 4 megaparsecs. And finally, it's great to have Lumos because it's very painful to devote 10 Hubble Space Telescope to only one star. But if you can do 20 of them at the same time, then it feels like the time is better spent somehow. Although each star is important. Anyway, yeah, so I'm out of time. I leave you with my conclusions, and thank you all for your patience.
Yep, thanks very much. So, yeah, so we should be moving on to the next talk. If there's a really urgent short question, go ahead. Otherwise, we can use the following time to discuss more about all this. Let's thank Miriam again. Okay, so final talk in the session. We are going to hear about synergies between Ulysses, massive stars, and the STSS-5 local volume mapper from Ida Warfoot. Take it away, Ida. And it's 20 minutes of 15.
It's a contributed.
It's contributed, so 10 plus 5.
Yeah.
Yeah.
Thank you. So thank you very much for sticking until the very end of this conference to hear about synergies between Ulysses, XQt, and the local volume mapper, which is part of the Sloan 5. This is a massive star talk, but hopefully it will trigger some ideas for the Loma star folks. And it's, I'm going to mostly talk about synergies regarding massive star feedback. But in order to illustrate some of the synergies that are possible, I am going to show preliminary results from a pilot study that involves the single star H2 region that you see in the yellow hexagon, which represents the field of view of the local volume mapper. Right, so summarizing what you have learned so far at this conference, Ulysses high mass stars and XQt are collecting massive star spectroscopy in the FUV, NUV, and all the way to the near IR for hundreds of massive star galaxies in 4 metal-poor galaxies, the Magellanic Clouds, NGC 3109, and Sextans A. And the sample of massive stars was selected to cover all luminosity classes from O2 to B1.5, but only supergiants will be observed for types B2 to B9. And XQt is going to obtain optical to near IR spectra for all of the Ulysses targets. Now, the really cool thing is that SDSS volume, local volume mapper will cover all of these galaxies, but the focus is on the nebular gas. And here you see people actually working on the telescopes that I'm going to describe. So these are not the only targets of LVM, but they will be covered by LVM. Okay, so a little bit about Sloan 5 first. So Sloan 5 has 3 mappers. The black hole mapper, which already has a data release, and that aims to study black holes, AGNs. extragalactic stuff. And then there's the Milky Way mapper that will obtain near IR and or optical spectra for millions of stars in the Milky Way. And that's to understand better the structure of the Milky Way. And then finally, the local volume mapper, which started very recently and which is ongoing. And that's what I'm here to talk to you about. OK, so the local volume mapper 1 takes place in the south. And it's an IFU survey. And it will target the Milky Way at 1 parsec spatial resolution. And then the small and large Magellanic Clouds at 10 parsec resolution. And other local volume galaxies at 100 parsec resolution. So the reason why there's a 1 there is because we hope that there will be an equivalent in the north. But that's a wild dream. Hopefully it will happen. OK, so the telescopes and the spectrographs. So there are 4 16-centimeter telescopes, which you see in the picture there. And with a DESI design spectrographs, they cover from 3,600 to 10,000 angstroms at a resolving power of 4,000. And there is one of the telescopes is the science telescope, and that's what's used for obtaining the observations. And then the sky fields and the spectrophotometry of stars are obtained with the other 3 telescopes. And the telescopes are located at Las Campanas Observatory in Chile. OK, so the field of view is this hexagon shape, and it has a diameter of about 30 arc seconds. So it's about like a full moon. And each of these hexagons has a fiber bundle of about 1,800 fibers, which you see here. This is an image from the simulator. And each fiber is about 35 arc seconds in diameter. And then the fraction of the field that the fibers feel is about 83%. So here's the status of the LMC LVM mosaic. In the background, you see an M-cell narrowband composite of the Large Magellanic Cloud. And so here, let me see if I can use these. That's the tiles of the LVM. And remember, in each one of these hexagons, we will have 1,800 spectra. And so this is very, very exciting. And now I would like to talk about preliminary results of a pilot program that we're doing, just to illustrate very concretely what some of the synergies can be between Ulysses XG2 and local volume mapper. So I'm going to talk about this star, 435, which you see here. This is the Small Magellanic Cloud. It's a narrowband composite. You see the bands there. It's main sequence 3F star. The F in parentheses means that it has a weak nitrogen 3 emission and helium 2 absorption. That's just the detail. Anyway, it has been observed as part of Ulysses XG2 and the early science LVM program. The star is producing an isolated H2 region, which makes the system really easy to study. And the aim is to determine if we can reproduce the nebular spectrum from LVM by using with a model that uses the ionizing spectrum that we inferred from modeling the Ulysses and XG2 data of the star. So that's the first thing we want to do. We're going to integrate the emission over the nebula and use a cloudy model to try to see if we put as input the ionizing spectrum of the star, if we can reproduce the spectrum. OK, so what you see here is a simulated, a simulation of what the LVM was supposed to see. The background image on the right is from M cells. It's an H-alpha image. You see the fiber bundle on top. And then on the right, you see the real LVM data, and you can sort of see the hexagonal shape. Now, currently, there's no dithering to fill in between the gaps of the fibers. So what you see on the left is a cube that has been, where we have interpolated between the fibers. There will not be dithering for all of the targets, but there will be dithering for some of the targets. The reason why there won't be dithering systematically is because the data sets would be humongous. All right, so, Daniel Pauly analyzed the Ulysses and XG2 data of the star. He had multi-epoch observations of the star, and this is what's shown here. So you see the 3 different epochs in 3 different colors, and he determined that there are no radial velocity shifts of the star, which is good because this means that it's presumably a single star, not a binary, and this makes it a much easier system to model. And then here are the beautiful XG2 optical spectra on top, and the UV Ulysses spectra from COS G130M and G160M at the bottom. And by feeding a stellar atmosphere model with the power code, you can infer the stellar parameters. And so it's a very luminous star, as you can see, with an effective temperature of 41 kilokelvin. And from the hydrogen lines, you can infer the surface gravity and the projected rotation. And then from the UV, you can get the mass loss, the terminal velocity, and then the ratio of X-ray to L-ball, the volumetric luminosity. Okay, so of course you cannot directly see the ionizing flux of the star. So this is something that you infer from the model, and this is what we need for modeling the H2 region. So here you see in this plot the resulting model. So the ionizing continuum is the shaded region. This is a model that includes X-rays, which are marked here between 2 and 25 angstroms. And so you can use already these to compute the star's production rate of hydrogen ionizing photons, so photons per second, by integrating the relevant region and transforming to luminosity, et cetera. And then, so we found that log Q for this is 49.44. And then you can also try to infer this QH1 by using the integrated H-alpha emission and with some assumptions. So the way you obtain this in this independent way is that you integrate the flux over the region, the H-alpha flux, and then you correct for the diffuse ionized background emission, the DIG, and then you correct for the stellar H-alpha absorption, which you see here, and which we got from XG2. And then we correct for reddening. We assume that there's no escape of ionizing photons from the region. We assume that all the Lyman alpha photons from 2 to 1 are absorbed. That's case B recombination. And then if we assume an electron density and a gas temperature, we can get QH. We still haven't done the exercise of using the actual density and gas temperature of, from LVM to infer this, because we just got access to the data very recently. But what we found is that we're off by a factor of 2. So the Q value from the H2 region inferred in this way is lower by a factor of 2. Now, what I didn't say is that this region is a monster. It's about 200 parsecs across, almost. So it must be very low density, and we will be able to check that. Now, take this with a grain of salt. These are preliminary values. But this is what we're finding for this region. And the next step, this is work that is ongoing, that is being done by graduate student Oscar Arangre, who should be online, is to do a library of cloudy models and try to see if we can reproduce the whole spectrum, integrated spectrum. Of course, we have spatial resolution, and we can do many other cool things, but this is just to give you an example of some of the synergies between X2, Ulysses, and LEM. Okay, so we have another isolated H2 region, another star there, and the data is good, so we're going to be doing something similar with this other one. It has lower luminosity. It's also in the SMC, and this will be the extent of the pilot program with the early release science observations, but we can extend these to many more targets. Now, that was the concrete example, but now let me give you a list of possible things that can be done that have to do with massive star feedback, and that Miriam has not mentioned yet. Understanding the feedback generating during the life and the deaths of high mass star is important because it facilitates the dissipation of protoplanetary disk, as we have heard this week. It enriches the interstellar and the circumgalactic medium. It drives the expansion of star-forming regions. It drives the disruption of molecular clouds, and it may be a key ingredient to understand scaling relations seen at kiloparsec size scales between the volume gas density and the star formation rate. It regulates the formation and dissolution of star clusters. Anyway, if your favorite application is not here, I'm sorry, but there's just so many. And then the other thing is, another application is that in local volume mapper, the focus is on the nebular gas. So you need to subtract the stellar continuum, okay? And for that, you need a stellar library. And the library that is right now implemented in the pipeline is the MassStar manga library, which is not optimized for massive stars. So we are eager to have the library that Lucy Mara Martins is putting together so that we can use it in local volume mapper to subtract the continuum and be able to study the nebular gas emission. Oh, wow. Well, thank you.
Yep. Thank you. Let's take a couple of questions. There's one there, and online, if there are any, we'll go to.
Can your lower Q value compared to the prediction be explained by dust absorption?
So the reddening is about 0.1 magnitude. It's not very high. But it's one of the things that we need to look into. Yeah, reddening is always something that could be affecting things.
And the absorption is very strong in the far UV.
Yes, of course.
Below the Lyman continuum.
Right. Yes, it's one of the things we're looking at. The other thing we're considering as well is that it's not such a round. It looks roundish, but it's not so round, and there's stuff, on the side. So we maybe need to improve the mask and make sure we're getting all the H alpha photons. Although I tried to do that already.
Anything online? Oh yeah. 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 Go ahead, Sally.
I did really wonderful work. I was struck that this is pretty much what the XShootU Working Group 9 is supposed to be doing. So I may be late to the party, but are you coordinating this with them, or are we supposed to be coordinating with you?
No, Grace Telford is coordinating this, and so we're all working on these together. And I'm sorry I forgot to mention, she's right there. And yeah, there's working group number 9. So yeah,
okay.
anybody
Great.
who wants to, who is part of that group, or if you want to join and you're not part of it, please just talk to me or Grace. Yes.
Well, I am part of it, but as I mentioned, I'm not as clued in as I should be, maybe. Thank you. Looks fantastic.
Thank you, Sally.
Okay, let's take one more comment.
Can you say something about how isolated the star is? How isolated are these regions? Can you really assume all the ionizing flux is coming from one star?
So let's see, I'm trying to find, yeah. So there's your region that's H. Oops, let's go back. The central part is the region in H alpha. There's some stuff here, but we can make a mask. I don't know if this gives you. Is this what you're asking? And when I measure the flux here, I mean, it goes down significantly here in between. But I cannot make like a circular aperture because then it would catch this. So I'm doing a collage of fibers.
Yeah. So we can continue the discussion later if as needed at the coffee break. But for now, I think we should move on. Let's thank all our speakers for this morning. And I'll hand it over to Julia now, and we'd start off the next session with Hab Worlds and other parallel sessions as needed.
Thank you, Ada. All right, so we talked a little bit about Hab Worlds this morning with Kevin and Miriam. So I don't know how many of you are aware of this NASA proposal call for precursor science cases. Raise your hand if you've already read about it. Okay, so not too many people. All right. So I'm not on the start for Hab Worlds, which is the science and technology and architecture review team, maybe something like that. Anyway, there's a group of people who are looking at kind of coordinating science requirements and architecture and all that kind of stuff. There are also, as Kevin mentioned, a bunch of working groups, both science and technology, that are also composed of community experts and working on science requirements. And still, NASA put out this call for precursor science, which is different from preparatory science. Maybe I should start with the scope. So I pulled out some of the language from the proposal call here. The NOIs are due at the end of March, so that's a couple weeks, and then the proposals are due in April. So you can read I'm also learning about this with you all because I am not involved in the START or TAG, but I am part of some working groups. And by the way, I will be posting the link to sign up for those working groups later if you don't have it already. So this Astrophysics Decadal Survey Precursor Science Program, which is ADSPS, so supports research in areas related to the recommendations of the Decadal Survey. What that means is it's not just Hab Worlds, but also the probes, X-ray and infrared, that were recommended by the Decadal Survey. Kevin provided a little bit more detail on the scope, which is really trying to capture from the community how some specific science cases could inform the architecture of Hab Worlds. And that means, for example, if you needed lumos to go into the optical, right? Right now, I don't think it's planned to do that, it's just UV, but if there was a strong science case to go into the optical, then you would want to build this case, and that could be such a proposal. So I'm going to read this. So the scope is really for these research proposals should describe how the scientific progress in the areas being investigated will either reduce the design and development risk from one or more of these future large missions, hub worlds in our case, or help define the requirements such missions must meet to enable transformative discoveries, and inform mission designs and trades when those activities begin. So it is pretty broad and not that specific. So I think there's scope to come up with science cases. At least I've heard a couple. There was the Lumos in the article, but possibly also some of the stellar mass accretion rate relation that Kelly talked about, and there was this gap, and that's due to just the design of Ulysses, because we were targeting just the brightest T-Tauri stars that we knew we could observe in not infinite orbits with Hubble. There are probably many, many more, and if you wanted to get a statistical sample of those, how faint would you have to go? And maybe you need to do some simulations and observations to determine that, and then derive, sensitivity requirements and such. So that could also be, for example, a precursor science case. NASA made sure to distinguish between precursor science and preparatory science. So the precursor science informed the use of the new observatory, but it doesn't mean let's do things that we can do now, and so that we don't have the science gap between Hubble and Hubble worlds. So these two things are different. And of course, it doesn't just include observations, but theory, simulations, lab investigations, and archival research. So again, pretty broad. So I mentioned the NOIs are due March 29, the proposals are due April 26. So I think the timing is kind of optimal to try to work as in collaborations while we're here to try to determine if or what precursor science cases we can come up with that would be a good outcome of Ulysses and to kind of move on and bridge the gap to hub worlds. I've put here some links to the proposal call and also the list of accepted precursor science programs from the 2022 calls. This is not the first one. There was one a couple of years ago, and there's a list of programs that were accepted there. So maybe at that point, I will actually show you those programs so that can be a little bit more concrete. A lot of those were for the probes. So for example, you see here, this was for the X-ray probe. These are just the abstract. Maybe I will share those in the Slack and give you a few minutes to take a look so you can get a more concrete ideas about the scope of these possible precursor science cases. And then when we're done with that, we'll regroup and people can try to maybe propose some ideas and then work as small groups to try to draft maybe an outline for a proposal. Does that sound good? Well, yeah, I'm ambitious. Let's set the bar high. We can have an A and B goal, but I think it's doable, right? If we can identify some strong precursor science cases, then you can move around and place yourself in small groups and work together to maybe have like an abstract or an outline or something like that that you can finish later. All right, so I'm going to go ahead and put those links in the Slack. And then you can go through the document quickly, get a sense of what's been accepted so far, and concretely what the scope is. Because I know the description in the call is a little vague. All right.
So what else we made that?
Oh yes, I'm sorry. And in parallel to that, as I mentioned yesterday, Joe, Elaine, and Rachel will be in the CAFECON to have, I would call it office hours on data products and Ulysses software. If you were at the data products session on Tuesday and you were maybe not able to follow along with the notebooks, or if you tried it since then and you got stuck, or if you would like to maybe learn about the additional notebooks that we mentioned to remake HLSPs, both from Ulysses products, but also non-Ulysses spectra, any cost and state spectra really, then go to the CAFECON and work with Elaine, Joe, and Rachel, and they can actually walk you through how to do this. Hmm? Oh, yes. Anyone online wants to go to the data products office hours? That's just so we know whether we need to connect the other room or not. Please speak up or put it in the chat if you need help with that. Yes. Yes, sorry, I didn't. Yeah. CafeCon is you walk all the way to the end of the cafe, make a right and a left, and the conference room's right there. No one online? Okay. So, thank you. And if you're working on the hub walls and you want to take a few minutes to go figure out some data product stuff, you're welcome to walk out, go talk to Joe, Rachel, Elaine, and then just come back in. All right, so let's take a few minutes to read accepted cases. Maybe like 10 minutes, and at 10:35, let's say, we'll start the actual work. I'm gonna go post the Slack, the link in the Slack now.
Julia, I have 2 questions.
Yeah.
So first question is, what's the typical length of one of these proposals? And second, what does it mean that the proposal was accepted? What are the implications?
So the implications is you get funding to do the work.
So no European.
I guess no Europeans, but you could partner with the American PIs, right? I mean, I think there's many of us in the room. Oh, it doesn't have to be PIs at American institutions, and you know the work can still get done. So I don't think it's a showstopper. We do this for Hubble all the time. Yeah. Do you have another question?
So after it gets accepted and you get the funding, what are you supposed to do? Meaning, do you need to work on the conceptual designs, or and do you, so you get enough funding for an engineer, or I don't know.
Yeah, I don't think the details of that were in the call. I'm gonna put the call too, and you can read it in detail. I read most of the call, which is actually pretty long, last night after dinner, and it wasn't great. But yeah, I think all the details are in there. I think I mean, there are deliverables. There's a plan of analysis and all that you need to put in the proposal. So it's like really the science, and then the plan of work, open science plan. There's like components like this. It's not there's also a page limit in there in the instructions. It's not a small amount of work, but I would say it's probably not as large as like a ROSIS ADAP or something like that. Not quite as involved. You have another question?
No, not just to know whether there are other things you could show what the other.
I'm going to put all the links in the Slack. Yeah, I mean, otherwise, yeah, it's going to be hard to do. So.
it's